Hello. Let's do this question. I did this question before, but I'm just going to try a different solution. So in this question, just a brief recap, you're given a graph and you want to find the minimum cost to get from node 0 to node n-1, where there are n nodes in the whole graph. You can just use Dijkstra's to do that, but there's an extra condition. You can't exceed the maximum time to get to this node. So you need to find a path. So you need to find a path that takes less than or equal to max time to get to this node. And out of all of those possible paths, return the minimum cost out of those. So we can, last time we did it using DP, where we asked the final node like in this case 5, node 5 with a max time of this. So we treat this as the state, and we query this state for what its min cost would be. We could get that to this state to recursively query its to other states, and so it would query the nodes neighboring this node. So the nodes neighboring this node we see is this 2 and a 4. There's a 2 here, and the max time that we want to consider only is max time minus 10, because it takes 10 units of time to get from node 2 to node 5. So if we can find the min cost to get to node 2 with a max time minus 10, then we know for sure we can get to the destination node with the min costs. But we also want to consider we can also consider the case where we get to the other node, node 4, with a max time of 15, and we could just get the min out of these two to be the answer to this state. So hopefully that makes sense. And we could just store the answer to these states in kind of a DP array or something like that. So that was the solution last time. And of course our base case was if node 0 if the node is 0 for whatever time, as long as it's greater than 0, then the cost would be equal to the fees of node 0. So that was the base case, so it doesn't loop infinitely. But this time we're going to try just use Dijkstra's. And Dijkstra's is good because it can find the minimum cost to get from one node to another node, but we just have to modify it so it doesn't consider paths that exceed the max time. But there's also a problem with that. I mean, that sounds simple, to just prune out paths that exceed the max time. But if you remember what Dijkstra's does, in Dijkstra there's a scene array. There's a scene array, so let's say if we've seen a node, then we won't consider that node again in an alternate path, but we do sometimes for this question. So how do we deal with that? So okay, let's get to paint. I'm going to draw an example. So let's say I have some nodes, some intermediate nodes. This is my destination node, this is my source node, and this is an alternate path node. And we have some edges going from those. Okay. Let's add some cost. So we know this is the destination, and this is the source. And let's say this has a cost of 1. So this is the cost of passing through this city. And this is the cost of passing through this city, same as these. But the time it takes to get from the source node to the next node is 10. And the time it takes to get from the next node to the next node is 10. And let's say this is 10. And let's say these are 2. This is 2. And the time and the fee that we have to pay to pass through this node is very large, like 100. And let's say the max time is equal to 100. Let's say 29. Okay, let's see what happens if you do a normal Dijkstra's algorithm. Well, first of all, we would start from the source, and we would go from this to this node. Right, and that makes sense because that's the only node, and we accumulate the cost as we go along. So the cost so far is 2 because we've passed through 2 cities. That's the cost of 2. Now at this node, we have 2 options. We could either go to this node here or this node here. So what we want to do first is we want to minimize the cost. So if we're minimizing the cost, then that means we want to go to this node because it would take 102 to get for this path, and it will take only 3 to get to this node here. So from this node, we only want to consider going to this node with a cost of 3. And we count the times as we go along as well. So the total time it takes to get to this node is 20 so far. All right. And then from here, we could either go to this node here with a cost of 103, or to this node with a cost of 4. Of course, it's best to go to this node with a cost of 4, but then, we realized the time it took to get this node is 30, which exceeds our max time, so we can't get to this node from here using this path. All right, so that's Dijkstra's, that's normal Dijkstra's, and then if we continue normal Dijkstra's, we would consider this node here because that's our only other option, with the cost of 102, and then it ends. Because we've already seen this node, Dijkstra's keeps a track of a scene array. And for the scene array of, let's say this is node 2. Node 2 is equal to true already. And for normal Dijkstra's, if you see that it's true, then we ignore it. But that's not what we want in this case. So we need to modify Dijkstra's to handle this as well. So let's see what we want to do here. If we instead keep track of the cost to get to a particular node, so the cost to get to node 2 would be equal to 3. And the time it took to get to node 2 is equal to 20. Alright. Then what we can do instead is sort the cost and the time together in the priority queue that we use for Dijkstra's. So if we have a tuple for the cost and the time, and also the node at the end, then we'll be sorting what node to do next by the costs first, and then by the time, and then by the node. But the node doesn't really matter. That's just extra information. So if we're at this point here, our only choice with normal Dijkstra's is to get to this node with a cost of 100, and the total cost so far is 102. Now instead of ignoring this node here, what we can say is, does going to this node decrease the time it takes to get to this node? Well, the time it takes to get to this node is 10 plus 2 plus 2, so 14, which is definitely less than 20, the other time it took to get to this node from the original path. If that's the case, if it decreases the time, then we want to modify the time here to change it to 14. And then we can push this node back onto the queue to consider it again. So we can get here at a lower time, and now we consider paths from this node. Yep, and that's pretty much it. So once we get to this node, then we can go to this node, no problem, because the time would then be 14 plus 10, so 24, which is less than 29, which is the max time. And once we reach the destination, then the cost to get we update the cost and time for the destination, and the cost would be then 102 plus 2 more, so 104. And 104 would be the answer in this case. So that's pretty much it for how you solve this question. How do you modify the Dijkstra's? Okay, so first thing we have to do is make sure we create the adjacency list, so that can be a vector of vectors, and that vector will contain just the adjacent node and the time it takes to get to that adjacent node. And here we can just say the maximum number. The maximum number of nodes is fees.size. No, that's the number of nodes, not the maximum number. And we could fill that out like we do. Go through all the edges, and adjacent E0 is equal to, nope, I want to push back the edge, which is E1, 2. So the edges are given like the source node, destination node, and the time. So the source to the destination with this time. But since it's bidirectional edges, we also want to consider it going the other way around. For some reason. Okay. That's that for the adjacency list. Now we also want to keep track of the times and the costs. How many would there be? It will be fees.size. But we want to initialize that to for everything to be int max. So initially it's infinite to get to everything, to get to each city, and the times same deal. The cost to get to the first node will be equal to the fee of the first city, and the time it takes to get to the first node is 0 because we start there. And we also need a priority queue. In priority queue, we can use a tuple. The reason we use a tuple because we need in each node that we store in the priority queue, the cost, the time, and the node itself. So we need a priority queue. And there's a priority queue of tuples that we can make it easier to say using by type defing a tuple of int by a call it a triplet. So I want a triplet here, and also need to, so by default priority queue sort it by largest to smallest, and when we poll we take from the front, so we would get the largest first, but we want to get the smallest first. So to do that, we need to say greater triplet as the last parameter of this template. But in the middle, because we want to fill out the greater part, we have to specify what the container will be, and that's PQ. I like to do it like this: auto PQ is equal to this type. Now the first node that's in there will be the source node, so pq.push we have the cost, the time, and the node. So the cost is the fees. Well, we've already filled it out here, so we can say cost 0 and time 0. And the node itself is 0. Okay, so now for Dijkstra's. For Dijkstra's, we need to continue while the queue is not empty. That means we will continue until any possible moves. There are no more possible moves that might decrease the cost and the time that we see here. So initially everything is int max. Now an easy way to grab all the cost, time, and node attributes, we can say cost, time, and node. From the pq.top. And then we also want to pop. Pop means we want to get rid of it. Now, if the time, actually, we could go through all the, so for all the edges, so for E in adjacent to node, let's say this is U, so this is U. The node, the adjacent node will denote by V, and that's going to be E1, E0. Okay, and the new fee, the cost, the new cost, say C, will be equal to the current cost plus the cost of the new node, so it'll be phi of V. The time would be the current time plus the time it takes to get to this node, this new node, and that's stored in E1 because we pushed that back here. Alright, and then we only want to consider this this node, if the time is actually less than or equal to the max time, so if the max time is, or if t is less than or equal to the max time, then only when we want to do stuff. If, you know, the cost, the new cost is less than the cost to get to node V, that means we want to consider it. We definitely want to push back. We want to push the cost, the time, and the node. And we also want to update the cost, because the cost is less than, we want to say the cost of node V would be C, and the time it takes to get to node V would be T as well. Now here's the part where we want to consider if the time is decreased, then we also push back to the queue. So the time, if the time is less than time V, times, then I want to update the time, and I also want to push back. Okay, let's think about this for a second. Why are we doing this and then doing an else if? And why are we only updating the time here and not the cost? It's because the cost may have increased by considering this time, but we only update the time because once we reach the destination node, as soon as we reach the destination node, the first time we see it is actually that would mean the time is less than or equal to the max time, and the cost that we see so far is actually the answer. Because for Dijkstra's, the first time you see something means that's the best answers for it so far. And that's why we don't need to update the cost here. And we do an else if because, as we saw here, first of all, we consider all the paths that decrease the cost as much as possible until we realize we can't get to the destination. So only then we can start considering paths that slightly increase the cost but have less time. So this kind of makes sense. And then at the end, we want to return the cost of the last node. So the last node will be fees.size minus 1. So int answer would be equal to this. But if it's not possible to get to the last node, then the cost to get to the last node will be still int max. So we want to return answer if it's equal to int max, then we want to return -1, like it says. Otherwise, then that means we just want to return answer. So this should be costs. Let's see if that works. It should be times. subscript throw PQ to push cost 0 times okay, so that seems to work for that. Let me try this case here. I've done this question before, so it's not like I figured it out just now. It took me a while. And hopefully this works as well. There were many attempts to get this right. So let's see if this version works. Yay.